The date is June 8, 1959. The place is 45,000 feet above the Mojave Desert. The air is thin, cold, and clear. But inside the cockpit of the B-52 bomber, the air is thick with tension. This is not a bombing run. This is a launch. Tucked tightly beneath the right wing of the massive 8-engine bomber hangs a machine that looks like a weapon forged in a nightmare. It is 50 feet long, painted a sinister, light-absorbing matte black. It has razor-stub wings that look too small to generate lift. It has a wedge-shaped tail that looks like a meat cleaver. It has no propeller. It has no jet intake. It is a missile with a window. This is the North American X-50, and the man strapped inside it, Scott Crossfield, is not an astronaut. Not yet. The word hardly exists in the public lexicon. He is a test pilot. He is an engineer, and right now he is sitting on top of 18,000 pounds of volatile fuel, waiting to be dropped like a bomb. Launch light is green. The voice crackles over the radio. Data recorder APUs up to speed. Crossfield checks his panel. He is encased in a silver pressure suit, a self-contained environment necessary because where he is going, the blood boils instantly in the veins. He is about to attempt the first unpowered glide flight of the X-15. He is about to drop a 30,000-pound brick of nickel-steel alloy from the sky and see if he can land it on a dried-up lake bed without killing himself. 3, 2, 1, drop. There is a loud metallic clunk as the shackles release. The X-15 falls away from the mothership. For a split second, there is weightlessness, that sickening lurch of the stomach as gravity takes hold. The B-52 banks hard to the left to get out of the way. Crossfield is alone. He is falling at 200 miles per hour, which for this aircraft is stall speed. It is falling like a stone. He has minutes, seconds, really to gain aerodynamic control, line up with the Rogers dry lake bed miles below, and execute a landing pattern that requires the precision of a surgeon and the nerves of a high-stakes gambler. There is no engine to save him. No go-around. He has one shot. This moment, this drop in the summer of 1959, marked the beginning of the most ambitious, dangerous, and successful flight research program in history. Before Neil Armstrong walked on the moon, before the space shuttle lifted off from Florida, there was the X-15. It was the bridge. It was the machine that taught America how to leave the atmosphere and, more importantly, how to come back without burning up. It flew faster and higher than any plane before or since. It was manned by a fraternity of pilots who viewed death not as a tragedy, but as a technical glitch to be solved. This is the story of the Black Bullet, the story of the men who fought a war against gravity, heat, and the absolute limits of human endurance. To understand the sheer audacity of the X-15, you have to look at the timeline. In the mid-1950s, the fastest planes in the world were struggling to reach Mach 2, twice the speed of sound. Aluminum airframes started to weaken at that speed due to heat friction. Jet engines began to choke. The US Air Force and the NAC, the predecessor to NASA, realized they were hitting a wall. They didn't just want to go a little faster, they wanted to leapfrog evolution. They issued a request for a proposal. Build a vehicle that can fly at Mach 6, 6 times the speed of sound, and reach an altitude of 250,000 feet. They wanted a plane that could fly into space and fly back. North American Aviation won the contract. But as their chief engineers sat down at the drafting tables in Los Angeles, they realized they weren't designing an airplane. They were designing a controlled explosion. The first problem was the heat. At Mach 6, roughly 4,500 miles per hour, the air molecules don't just flow over the wing. They smash into it. The friction creates a shock wave that heats the nose of the aircraft to 1,200 degrees Fahrenheit. The leading edges of the wings glow cherry red. Aluminum melts at 1,220 degrees. If they built the X-15 out of standard aircraft metal, it would turn into a streak of molten slag before the fuel tank was empty. So, they turned to a material called Inconel X. It is a nickel-chromium alloy, incredibly dense, incredibly hard, and incredibly heat-resistant. It was typically used for the inside of turbine engines and blast furnaces. No one had ever built an entire airplane out of it. It was a nightmare to work with. It destroyed drill bits. It was heavy. It forced the engineers to invent new welding techniques from scratch. The skin of the X-15 wasn't riveted. It was welded solid to withstand the thermal expansion. When the plane got hot, the metal would expand, and the plane would actually grow in length by several inches. The engineers had to design expansion joints into the plumbing and the frame, allowing the machine to stretch and groan without snapping apart. The second problem was the engine. A jet engine needs air to breathe. But the X-15 was going where there is no air. It needed a rocket. The specifications called for an engine that could produce 57,000 pounds of thrust. That is 500,000 horsepower, equivalent to the power of 2 Navy destroyers packed into a fuselage the size of a school bus. They built the XLR-9. It was a monster. It burned a mixture of anhydrous ammonia and liquid oxygen. Most rockets of the time were all or nothing. You lit the fuse and it burned until it was empty. But the X-15 pilots were pilots, not passengers. They demanded a throttle. They wanted to be able to control the power, to shut it down, to restart it. The XLR-99 was the first large throttleable rocket engine. It was a masterpiece of engineering, but it was also a bomb. Sitting in the cockpit, the pilot was essentially straddling a tank of high explosives with a torch in his hand. The pilot's office, the cockpit, was a lesson in claustrophobia and utility. There were no digital screens, no touchpads. It was a wall of analog gauges, toggle switches, and circuit breakers. The pilot sat in an ejection seat that was essentially a rocket itself, designed to blast him clear of the aircraft at supersonic speeds if things went wrong. But everyone knew the dark truth. At Mach 4 or Mach 5, ejecting was likely a death sentence. The wind blast would break every bone in your body. The heat would melt your suit. The seat was there for low-altitude emergencies. Up high, you rode the ship down, or you died with it. Let's go back to the flight line at Edwards Air Force Base. It is the spiritual home of American aviation, a place of blinding white salt flats, jagged mountains, and a culture of stoic professionalism. The pilots selected to fly the X-15 were the best the nation had to offer. There was Scott Crossfield, the intense intellectual who knew more about the plane's engineering than the builders. There was Joe Walker, a chain-smoking World War II veteran with a calm, folksy demeanor that hid nerves of steel. There was Robert White, the Air Force ace, and there was a young, quiet civilian engineer named Neil Armstrong. Armstrong was different. He wasn't a showboat. He didn't care about records for the sake of records. He cared about the data. He wanted to understand the math of the flight. His colleagues respected him, but they also knew he was calculating risks in a way that others weren't. He treated the X-15 not as a wild stallion to be tamed, but as a complex equation to be solved. The early flights were fraught with danger. The big engine, the XLR-99, wasn't ready yet, so for the first year, they flew with 2 smaller engines from the X-1 program strapped into the bay. It was like putting a lawnmower engine in a Ferrari, but it was enough to test the aerodynamics. November 5th, 1959. Flight number 3. Scott Crossfield is in the cockpit. He drops from the B-52. He lights the engines. Explosion. A fire warning light flashes red on the dashboard. An engine fire in a rocket plane is usually fatal. The fuselage is packed with fuel lines. Crossfield shuts down the engines immediately. He is heavy, full of fuel. He has to land, and he has to land now. The emergency procedures for the X-15 are complex. You have to jettison the fuel, dumping the ammonia and the liquid oxygen overboard to lighten the load and reduce the explosion risk. Crossfield flips the dump switches. White vapor streams from the back of the plane. He is falling toward Rosamond Dry Lake. It is smaller than the main lake bed at Rogers. He is coming in hot. Without the fuel weight, the landing speed is fast, over 200 miles per hour. The X-15 doesn't have normal landing gear. Tires would melt at high speeds. Instead, it has a nose wheel and 2 steel skids in the back. It is designed to slide to a halt like a sled. Crossfield lines up. He flares the nose. The rear skids hit the dried mud. Crunch. The nose slams down. But instead of rolling, the nose gear collapses. The front of the plane smashes into the lake bed. The X-15 breaks its back. The fuselage buckles just behind the cockpit. The plane slides across the desert in a cloud of dust, a broken, twisted wreck. The rescue trucks race across the flats. The fire crews are terrified the remaining fuel will detonate, but the canopy opens. Crossfield climbs out, unhurt. He looks at the broken bird. The engineers are devastated. This was X-15 number 1. They thought the program might be over. But Crossfield was calm. "Fix it," he said, and they did. They dragged it back to the hangar, welded it back together, reinforced the fuselage, and kept flying. That was the ethos of the program. You break it, you fix it, you fly it again. By late 1960, the big engine, the XLR-99, was finally ready. Now, the gloves were off. The X-15 was no longer underpowered. It was overpowered. November 15, 1960. Scott Crossfield takes the X-15 up with the new engine. This is the first time the full power of the beast will be unleashed. He drops. He ignites. The acceleration is instantaneous. It is violent. The throttle response is terrifying, Crossfield reported. Unlike a jet, which spools up slowly, the rocket hits you with 57,000 pounds of thrust in milliseconds. The pilot is pinned to the seat, unable to lift his arms. He has to fly using a side-stick controller, moving only his wrist, because the G-forces make it impossible to reach the center stick. The X-15 shot forward, shattering Mach 2, Mach 3. Crossfield shut it down early. They were just testing. But they knew they had built a monster. Now, the competition began in earnest. The space race was heating up. Yuri Gagarin launched in April 1961. Alan Shepard followed in May. The capsule astronauts were getting the glory. They were on the covers of magazines. They were having ticker tape parades. But at Edwards, the X-15 pilots were doing something the capsule astronauts couldn't do. They were flying into space. A capsule is a bullet. You aim it, fire it, and it falls. The astronaut is a passenger. The X-15 was a plane. The pilot controlled the pitch, the yaw, the roll. He controlled the engine shutdown. He controlled the re-entry angle. If he messed up, he didn't just land off target. He skipped off the atmosphere into solar orbit or burned up. The rivalry between the capsule guys and the wing guys was real. The X-15 pilots viewed themselves as the true aviators. They were flying the last aircraft where the pilot's skill was the only computer on board. Let's dissect a typical mission profile to understand the workload. The flight plan for a high-altitude run is a masterpiece of energy management. The drop occurs at 45,000 feet and 500 miles per hour. The pilot lights the engine. He pulls back on the stick to a precise angle, say 38 degrees. He holds that angle while the G-forces build to 4 Gs. The sky turns black. at a specific velocity and altitude calculated by slide rules on the ground. He shuts down the engine. He is now coasting. He is a projectile. As he leaves the dense atmosphere, the aerodynamic controls, the rudders and ailerons on the wings, stop working. The air is too thin. The plane becomes sluggish. He switches to the reaction control system, RCS. These are small thrusters in the nose and wingtips that shoot jets of hydrogen peroxide steam. Stussed. He is now flying a spacecraft. He uses the thrusters to keep the nose pointed correctly. This is critical. If the nose drifts sideways while he is in space, when he hits the atmosphere on the way down, the plane will disintegrate. He has to keep the needle pointed into the wind that isn't there yet. He reaches the top of the arc, the apogee, 200,000 feet, 300,000 feet. He is weightless for about 2 or 3 minutes. He sees the curve of the Earth. He sees the black void, but he cannot sightsee. He is setting up for the most dangerous part of the flight, re-entry. He is falling back toward Earth at Mach 5. He has to pull the nose up to create drag. He uses the entire bottom of the plane as a brake. The G-forces build rapidly. 5 Gs. 6 Gs. The heat builds. The nose glows orange, then yellow, then white. The pilot is fighting to keep the plane level while his body is being crushed and the cockpit temperature rises. Then, as he slows down below Mach 3, the air becomes thick enough for the wings to work again. He transitions back from spacecraft to aircraft. He has to find the lake bed. He has no engine. He has one chance to line up the glide. He spirals down, bleeding off energy, dropping the landing gear at the last second and skidding to a halt in the dust. The entire flight takes about 10 minutes. But in those 10 minutes, the pilot makes more decisions than an airline pilot makes in a career. The program pushed boundaries that no one expected. They discovered hotspots. They found that the shock waves from the nose and the wings could interact, creating localized zones of intense heat that could melt through the skin like a blowtorch. On one flight, pilot Bob White came back with the leading edge of the wing melted and deformed. The engineers were horrified. If he had flown for 10 seconds longer, the wing would have sheared off. They discovered that at hypersonic speeds, the air can become electrically charged, interfering with radio signals. They were writing the textbook on hypersonics chapter by chapter, flight by flight. And then there was Neil Armstrong. Neil was known for his engineering brain. He wanted to push the X-15 not just for speed, but for understanding control. April 20th, 1962, Flight 3. 5197. Neil is in X-15 number 3. The mission is to test a new adaptive flight control system. He drops, he climbs. But during the ascent, he holds the nose up a little too long. The G-limiter, a safety device, keeps the nose down, but Neil fights it to test the limits. When the engine cuts off, he is higher than planned, 207,000 feet. He sails over the top of the arc. As he begins to fall back down, he pulls up to test the G-limiter again, but he bounces. Like a flat stone skipping on water, the X-15 hits the dense atmosphere and skips back up. He is not slowing down. He is maintaining his speed, Mach 3, and his altitude. But he is still moving south. He passes over the landing site at Edwards. He passes over Los Angeles. He is flying over the Rose Bowl. Over Pasadena. He is miles off course. He looks down and sees the sprawl of the city, the swimming pools, the freeways. He is a silent, black menace flying over unsuspecting millions at 3 times the speed of sound. Neil realizes he is in trouble. He is too far south. If he turns around now, he might not have enough energy to glide back to the lake bed. He might crash in the suburbs or the ocean. Most pilots would panic. Neil gets quiet. He banks the plane hard to the left. A massive, sweeping turn over Southern California. He is bleeding off speed in the turn, trading velocity for a change in direction. He points the nose back north. He is 45 miles south of the base. He is gliding. He checks his instruments. Can he make it? He cleans up the drag. He flies efficiently. He creeps over the San Gabriel Mountains, clearing the peaks by a few thousand feet. He sees the lake bed. He comes in straight in. No circling. He drops the gear. He hits the dust. It is the longest flight of the X-15 program in terms of duration. When he climbs out, he simply says, "The longest way around is the shortest way home." It was a close call. A very close call. It showed that even the best pilots could be humbled by the physics of hypersonic flight. But the X-15 had not yet claimed a life. It had broken bones, it had crumpled metal, but it had not killed yet. The laws of probability were catching up. You cannot dance on the edge of a volcano forever without getting burned. As the program moved into the mid-60s, the goals became more aggressive. Higher, faster. They wanted Mach 6. They wanted Mach 7. They were modifying the planes, adding external tanks, adding experimental coatings. They were pushing the envelope until it tore. And one day, over the high desert, the envelope would tear apart completely, taking a good man with it. But before the tragedy, there would be the triumph of speed. The day the X-15 became the fastest machine ever built. By 1962, the X-15 program had moved beyond the proof-of-concept phase. They knew the plane could fly. They knew the engine worked. They knew a human being could control a rocket at 3,000 miles per hour and bring it back to Earth. The initial questions had been answered. Now the mission parameters shifted. The goal was no longer just to survive. The goal was to dominate. The Air Force and NASA wanted to push the envelope until it tore. They wanted to find the absolute limits of speed and altitude. They wanted to turn the dial all the way to the right and see what happened. This phase of the program introduced a new enemy. In the early days of aviation, the enemy was drag. Then, it was the sound barrier, the compressibility of air that shook planes apart at Mach 1. But at Mach 4, Mach 5 and beyond, the enemy changes. The enemy becomes heat. This is the thermal barrier. It is a relentless physical war. When an object moves through the atmosphere at hypersonic speeds, 5 times the speed of sound, the air molecules cannot move out of the way fast enough. They are trapped against the skin of the aircraft. They are compressed violently. This compression excites the molecules, causing them to release energy in the form of heat. It is a blast furnace generated by pure velocity. At Mach 3, the nose of the aircraft reaches 600 degrees Fahrenheit. At Mach 5, it hits 1,200 degrees. At Mach 6, the stagnation point temperatures, the heat at the very tip of the nose and the leading edges of the wings, can exceed 1,300 degrees. Steel softens at 1,000 degrees. Aluminum loses its structural integrity long before that. The Inconel X nickel alloy of the X-15 was tough, but even it had a breaking point. The engineers calculated that if they wanted to go faster than Mach 6, the plane would essentially begin to glow. It would lose its rigidity. The wings might warp. The control surfaces might seize. The pilot would be flying a noodle. To break the world speed record, they couldn't just use the standard X-15. They needed a hot rod. They needed a modified beast. Fate provided them with the chassis. On November 9th, 1962, pilot Jack McKay was flying X-15 number 2. He experienced an engine failure shortly after drop. He had to make an emergency landing at Mud Lake, Nevada. He came in heavy, full of fuel. The landing gear collapsed. The plane slid across the lake bed, flipped over on its back, and was smashed. McKay was injured. He suffered crushed vertebrae that would plague him for the rest of his life, but he survived. The plane, however, was a wreck. Instead of scrapping it, the Air Force decided to rebuild it. But they didn't just repair it, they mutated it. They lengthened the fuselage by 29 inches to accommodate a tank for liquid hydrogen for future scramjet tests. They reinforced the landing gear, and, most importantly, they added external fuel tanks. The standard X-15 carried its fuel internally, but to reach Mach 6, the engine needed to burn longer. So the engineers strapped two massive drop tanks to the sides of the fuselage. One held anhydrous ammonia, the other liquid oxygen. These tanks carried an additional 13,500 pounds of propellant. They looked like giant bombs strapped to the side of the Black Needle. The plan was to drop from the B-52, light the engine using the external fuel first, climb to 70,000 feet, jettison the empty tanks, and then burn the internal fuel to push the speed into the history books. This new aircraft was designated the X-15A-2, but the extra fuel wasn't enough. They still had the heat problem. If they pushed this new configuration to its theoretical limit of Mach 8, the metal skin would melt. They needed a heat shield. The solution they came up with was ugly, messy, and effective. They decided to coat the entire airplane in an ablative material. An ablator is a substance designed to burn away. As it heats up, it chars, and the char carries the heat away from the airframe. It is the same principle used on the re-entry shields of the Gemini and Apollo capsules. They used a material called molten Ma-25S. It was a pink spray-on foam. Imagine covering a sleek, terrifying fighter jet in pink insulation foam. The ground crews sprayed it on by hand. It was toxic. It smelled terrible. It dried into a hard, cork-like consistency. When the job was done, the menacing black bullet was gone. In its place sat a lumpy, eraser-pink monstrosity. The pilots hated it. It looked ridiculous. To make matters worse, they had to seal it with a white topcoat to protect the foam from moisture. So now the X-15 was a white ghost. But the indignity didn't stop there. The ablator would char and streak during flight, covering the windows in black soot. The pilot would be blind. To solve this, the engineers installed a mechanical A-lid over the left window of the canopy. It was a metal shutter. The pilot would fly the entire high-speed run with one eye blocked, staring at his instruments. Only just before landing would he open the eyelid to see the runway. It was a coffin with a periscope, and Pete Knight was the man chosen to fly it. October 3rd, 1967, the day of the absolute speed record. Major William Pete Knight was a seasoned test pilot, a man known for his precision. He walked out to the white X-15A-2. He climbed into the cockpit. The suit technician strapped him in. The canopy, with its bizarre metal eyelid, was lowered. The B-52 mothership hauled the heavy load into the air. The takeoff was sluggish. The X-15, with its full external tanks, weighed over 50,000 pounds. It was the heaviest object ever dropped from a wing. They climbed to 45,000 feet. The desert below was a brown blur. Launch, launch. Knight hit the switch. The shackles opened. The heavy white plane dropped. He lit the XLR-99 engine. The response was sluggish at first because of the weight, but as the external tanks drained, the acceleration built. He climbed steeply. At 67 seconds into the flight, he was at Mach 2. The external tanks were empty. He hit the jettison switch. Thump, thump. The two giant tanks peeled away, falling toward the desert floor. Now the X-15 was clean. It was light, and the engine was still burning at full power. The acceleration that followed was violence incarnate. Mach 3, Mach 4, Mach 5. Knight was pinned to his seat. The G-meter read 2 Gs, then 3 Gs straight back into the chest. He wasn't just moving fast, he was outrunning the sun. The shockwave cone off the nose was swept back so tight it was almost touching the canopy. The white ablative paint began to burn. Inside the cockpit, Knight could hear it. A strange, sizzling, popping sound. It was the sound of the plane shedding its skin. The soot from the burning paint began to coat the windows. The right window went black. The left window was covered by the metal eyelid. Knight was flying on instruments alone, guided by the needles and the voice of mission control. Mach 6. He was traveling at 1 mile per second. He pushed the throttle. The engine screamed. Mach 6.7, 4,520 miles per hour. He held it there. The vibration was intense. The airframe was groaning, but something was going wrong at the back of the plane. The engineers had attached a dummy scramjet engine to the lower ventral fin, a test article to see how air flowed into an engine at hypersonic speeds. They didn't realize that they had created a blowtorch. The shockwave coming off the scramjet interacted with the shockwave from the pylon. This is called shock-shock interaction. It focuses the energy of the airflow like a laser beam. The temperature in that localized spot spiked to 2,700 degrees Fahrenheit. It cut through the white paint. It cut through the pink foam. It cut through the Inconel skin. It began to melt the structural ribs of the tail. The plane was being cut in half by its own shockwave. Warning lights flickered on the panel. Engine shut down, Knight said. He cut the fuel. The acceleration stopped instantly, throwing him forward against his straps. He was now a glider, moving at Mach 6, with a hole melting in his tail. As he decelerated, the heat load reduced, but the damage was done. The scramjet broke loose and fell into the desert. Knight managed to keep the plane stable. As he approached the landing field, he opened the mechanical eyelid. The fresh glass was clear. He could see the lake bed. He brought the white ghost down for a landing. The skids hit the dust. The slide was long and fast. When the plane finally stopped and the ground crews arrived, they were horrified. The beautiful white bird looked like it had been held over a lighter. The paint was charred black and streaked. The bottom of the tail was eaten away, melted into slag. If Knight had flown for another 30 seconds, the tail would have disintegrated and the plane would have tumbled into oblivion. Pete Knight climbed out. He was the fastest man alive. He had flown Mach 6.7. It is a record that still stands for a piloted, powered aircraft. But the X-15A2 never flew that fast again. They had found the wall. The thermal barrier was real, and it bit back. While Pete Knight was chasing speed, other pilots were chasing altitude. This was the second front of the war on gravity. The Air Force wanted to know, can a plane fly into space? The definition of space is debated. The FAI, Fédération Aéronautique Internationale, defines it as the Kármán line 100 kilometers or 62 miles up. The US Air Force defined it as 50 miles. The X-15 was designed to shatter both. Flying for altitude is a completely different discipline than flying for speed. To go fast, you fly level. To go high, you fly a ballistic arc. You drop from the B-52, light the engine, and pull the stick back. You pull the nose up to a steep angle, 38 degrees, sometimes 40 degrees. You are climbing a mountain of air. The sky changes color rapidly. Blue, purple, black. At 100,000 feet, the engine burns out. You are now a projectile. You are coasting up the hill. Momentum carries you. 150,000 feet, 200,000 feet, 250,000 feet. This is where the X-15 becomes a spaceship. The air density is practically zero. The ailerons on the wings, the flaps that control roll, are useless. You can move the stick all the way to the left and the plane won't bank. It's like trying to steer a boat with a rudder that is out of the water. This is the most critical phase of the flight. If the plane starts to drift, if the nose wanders off center, you are in mortal danger. If you enter the atmosphere sideways on the way down, you die. So the pilot switches to the RCS reaction control system. He uses a controller on the left side of the cockpit. It looks like a small pistol grip. He moves it, and small valves open in the nose and wings. Hydrogen peroxide flows over a silver catalyst screen. It instantly decomposes into superheated steam and oxygen. A jet of steam fires in the vacuum. Newton's third law kicks in. The nose moves. The pilot is now flying by reaction. He has to be gentle. In a vacuum, there is no air resistance to stop a rotation. If you start a roll, you will roll forever, unless you fire an opposite thruster to stop it. It is a delicate ballet. The master of the altitude flights was Joe Walker. Walker was a civilian pilot for NASA. He was a small man, wiry, with a receding hairline, and a permanent cigarette in his hand. He looked like a high school physics teacher, but in the cockpit he was a magician. On August 22nd, 1963, Walker took X-15 number 3 up for the ultimate climb. Flight 32236. He dropped. He burned. He pulled the nose up. The engine shut down, but he kept climbing. He passed the Air Force limit of 50 miles. He passed the Kármán line of 62 miles. He peaked at 354,200 feet. That is 67 miles high. He was deep in the mesosphere. He was undeniably in space. He looked out the window. It's a very dark black blue, he radioed. And the Earth is bright. It's brilliantly bright. He could see the curvature of the Earth stretching from Canada to Mexico. He was weightless for nearly 5 minutes. In the cockpit, a pack of cigarettes he had tucked into a pouch drifted loose and floated in front of his face. He grabbed them. He was a spaceman. But the descent is the price. Falling from 67 miles high means you hit the atmosphere with tremendous energy. Walker had to set up the re-entry angle perfectly. If he was too steep, the G-forces would kill him. If he was too shallow, he would skip off. As he fell, the G-meter climbed. 5 Gs. It feels like an elephant sitting on your chest. 6 Gs. Your vision grays out. You have to grunt to force blood to your brain. 7 Gs. Most people pass out at 5. Walker held it. The plane groaned. The metal expanded. He rode it down, transitioning from rockets to flaps, from space to air, from silence to the roar of the wind. He landed perfectly on the dry lake. When he climbed out, he didn't make a speech. He just lit a cigarette. But these high-altitude flights revealed a new physiological horror. The doctors monitored the pilots' heart rates. They expected them to be high, maybe 120 or 130 beats per minute. They were shocked by the data. During the launch and re-entry phases, the pilots' heart rates regularly spiked to 170, 180, sometimes 190 beats per minute. This is near the maximum human limit. This wasn't just adrenaline. This was the body fighting for survival. The workload in the cockpit was immense. The pilot was performing a physical workout equivalent to sprinting a mile while sitting still, strapped into a chair, doing complex calculus in his head. The physical toll was cumulative. The vibration of the engine could blur vision. The ebbs-out G-forces during deceleration pulled the eyes forward against the lids. And then there was the radiation. At 300,000 feet, you are above the protective layer of the atmosphere. You are exposed to cosmic rays. The X-15 pilots were technically radiation workers. They wore dosimeters. They were soaking up gamma rays every time they went high. By the mid-1960s, the X-15 program had achieved everything it set out to do. It had flown fast. It had flown high. It had proven that humans could pilot a spacecraft, but the machines were getting tired. X-15 number 1 had flown over 70 times. The metal was fatigued. Micro cracks were appearing in the frame. The pilots were getting tired too. They were aging, and the technology was becoming obsolete. The space race had moved on. NASA was launching Gemini capsules. They were building the Apollo Saturn V. The X-15, with its analog dials and mechanical valves, began to look like a dinosaur. But there was one more tragedy to come. One final reminder that the desert doesn't forgive mistakes. It involved the newest plane, the X-15 number 3, and a pilot named Mike Adams. Adams was a brilliant engineer, but he was new to the program. On November 15, 1967, he took Flight 36597. He climbed to 266,000 feet. He made astronaut, but at the top of the arc, something went wrong. An electrical disturbance, a computer glitch, and a moment of distraction. The plane began to drift sideways. Adams didn't catch it in time. As he fell back into the atmosphere, the X-15 was not pointed forward. It was pointed at a 15-degree yaw. At Mach 5, flying sideways is a death sentence. The air grabbed the plane. It snapped into a hypersonic spin. Spinning at 3,000 miles per hour, 5 Gs positive, 5 Gs negative, back and forth. Adams was being thrashed inside the cockpit like a doll. He fought the controls, but the system was overwhelmed. The telemetry on the ground showed the plane descending into the thick air, spinning wildly. "Break it off, Mike," the communicator shouted, "but you cannot break off gravity." At 62,000 feet, the structural limits were exceeded. The X-15 shattered. It broke into thousands of pieces, raining down over the town of Johannesburg, California. Mike Adams didn't stand a chance. It was the only fatality of the program. It was a brutal end to a glorious era. It proved that no matter how good the pilot, no matter how strong the metal, the war on gravity is never truly won. You just survive the battles. But before the end, before the museums claimed the blackbirds, there were moments of pure, unadulterated engineering magic. There was the day the X-15 flew autonomously. There was the day they tested the insulation for the Saturn V. Every bolt on the Apollo rocket owed something to the X-15. The pilots knew they were the last of a breed. The capsule astronauts were spam in a can, passengers. The X-15 pilots were aviators. They flew the wings off the beast, and they did it with a slide rule in one pocket and a pack of cigarettes in the other. As we prepare to look at the legacy of this machine in the next part, remember the image of the white X-15 scorched black by speed. Remember the heart rate of 190. Remember the sound of the metal cooling on the lake bed. Ping, ping, ping. The sound of a machine that had been to hell and back and was ready to go again. To operate at the edge of the envelope is to accept a specific contract with physics. If you execute the procedures perfectly, the laws of aerodynamics will sustain you. If you deviate, even by a fraction of a degree, those same laws will destroy you. The X-15 program had flown nearly 200 missions with an incredible safety record. There had been hard landings, broken fuselage spines, blown engines, and shattered windshields, but the pilots had always walked away. They had begun to feel invincible. The machine was tough. The men were tougher, but in the autumn of 1967, the probability curve finally caught up with the program. The desert, which had been patient for 8 years, finally demanded a sacrifice. This chapter of the story is not about records. It is about the anatomy of a disaster. It is a forensic look at Flight 36597, the day the X-15 was torn apart by the very sky it was designed to conquer. And it is about the black year of Edwards Air Force Base when the test pilot fraternity lost its brightest stars, not to enemy fire, but to the unforgiving nature of the test. To understand the crash of X-15 number 3, we must first understand the unique danger of the hypersonic spin. In a standard jet fighter, a spin is dangerous but recoverable. You cut the power, you neutralize the stick, you stomp on the opposite rudder to stop the rotation, and you dive to gain airspeed. It is a terrifying maneuver, but it is standard curriculum in flight school. But at Mach 5, at an altitude of 50 miles, a spin is a death sentence. At those speeds, the airframe is subjected to dynamic pressure, represented by the symbol Q. When the X-15 is flying straight and level like an arrow, it slices through this pressure. But if the plane turns sideways, if it yaws more than 10 degrees, the air catches the broadside of the fuselage. Imagine driving a car at 100 miles per hour and suddenly turning the steering wheel 90 degrees. The car flips. Now imagine doing that at 3,500 miles per hour. The aerodynamic forces are so immense that they don't just flip the plane, they shred it. The structural limits of the nickel alloy frame are exceeded in milliseconds. The plane doesn't crash, it disintegrates. Major Michael J. Adams was the man in the cockpit on November 15, 1967. He was not a rookie. He was a decorated Korean War veteran, a brilliant engineer with a degree in aeronautical engineering, and one of the most respected pilots in the Air Force. He was known for his quiet, analytical demeanor. He was the type of man who checked the checklists twice. He was flying X-15 number 3, the most advanced aircraft in the fleet. It was equipped with a new experimental flight control system called the MH-96. This system was an adaptive autopilot. In the thin air of space, where the standard controls were mushy, the MH-96 was supposed to automatically fire the reaction control thrusters to keep the plane steady. It was designed to help the pilot, but on this day, it would kill him. The launch was normal. Adams dropped from the B-52, lit the candle, and climbed. He hit his marks perfectly. He shut down the engine at the top of the arc, coasting to an altitude of 266,000 feet, over 50 miles high. He had earned his astronaut wings, but as he crested the apogee, floating in the silence of space, an electrical disturbance flickered through the ship. A camera experiment on board arced, sending a spike of voltage through the aircraft's wiring. The lights on the instrument panel blinked. The computer reset. Adams was distracted. This is the startle factor. In the cockpit, a pilot's attention is a finite resource. When a warning light flashes, the eyes go to it. The brain engages with the problem. For a few critical seconds, Adams was troubleshooting the electrical glitch. He didn't notice that the plane was drifting. The nose of the X-15 began to yaw slowly to the right. In the vacuum of space, there is no wind to straighten the plane out. If you turn, you stay turned. The nose was now pointing sideways relative to the flight path. The X-15 was flying like a crab, skidding through the void. As the plane began to fall back toward the atmosphere, Adams looked up and realized his orientation was wrong. He grabbed the stick to correct it. But here lies the tragedy. The MH-96 adaptive control system was confused. The electrical spike had scrambled its logic. When Adams tried to push the nose left, the computer fought him. It fired the thrusters to the right. Man and machine were wrestling for control of a falling bullet. The plane hit the upper layers of the atmosphere at 230,000 feet, moving at Mach 5. The air grabbed the sideways fuselage. The spin began. It was violent beyond description. The X-15 snapped into a rotation that generated 15 Gs of force. Most humans black out at 5 or 6 Gs. At 15 Gs, the blood is forced out of the brain instantly. The internal organs are crushed against the rib cage. The telemetry data sent back to the control room was a nightmare. The needles on the consoles were pegging off the charts. "I'm in a spin," Adams radioed. His voice was strained, guttural, the voice of a man being crushed by a giant hand. The mission controllers were helpless. "Mike, disengage the damper. Disengage," the Capcom shouted. If Adams could turn off the computer, he might be able to fly it manually. But the G-forces were pinning his arms. He couldn't reach the switch. The X-15 fell from 230,000 feet to 62,000 feet in a matter of seconds. It was a spinning meteor. At 62,000 feet, the dynamic pressure, the cube reached a critical point. The air was too thick, the speed too high. The structural integrity of the Inconel X failed. The plane shattered. It didn't explode in a ball of fire. It simply came apart. The fuselage snapped into pieces. The wings were torn off. The engine blocks separated. The debris field rained down over 50 square miles of the Mojave Desert, near the gold mining town of Johannesburg. The cockpit section, with Adam still strapped inside, fell tumbling to the earth. It impacted the desert floor at terminal velocity. There was no parachute. There was no ejection. The recovery teams found the wreckage hours later. It was a scene of devastation. The pride of the American aerospace program was reduced to twisted scrap metal scattered among the sagebrush. They found the camera instrument. Miraculously, the film survived. When they developed it later, they saw the final moments from the pilot's perspective. The instrument panel shaking violently, the horizon spinning like a top, and then the reflection of the Earth in the glass dial of the altimeter. Major Mike Adams was posthumously awarded his astronaut wings. He was the first and only fatality of the X-15 program, but his death signaled the end of the era of innocence. The engineers realized that they had pushed the analog technology as far as it could go. The human pilot, unaided by digital computers, could no longer keep up with the machine. But the tragedy of Mike Adams was compounded by another loss, one that struck even deeper into the heart of the test pilot fraternity. It involved a man who was the soul of the X-15 program, Joe Walker. Joseph Albert Walker was a legend. He was the cowboy of the stratosphere. He flew the X-15 higher than anyone else, twice exceeding 60 miles in altitude. He was a civilian pilot for NASA, a chain smoker, a man with a crooked smile and nerves of ice. He was the one who had flown the highest flight. After retiring from the X-15 program, Walker continued to fly chase planes and other test vehicles at Edwards. On June 8, 1966, a year before the Adams crash, Walker was flying an F-104 starfighter. He was flying chase for a photo shoot. The subject of the photo was the XB-70 Valkyrie. The Valkyrie was the most beautiful, terrifying bomber ever built. It was a massive, white, delta-winged supersonic nuclear bomber capable of Mach 3. It looked like a paper airplane folded by a god. It was huge, 189 feet long. General Electric, the engine manufacturer, wanted a publicity photo. They arranged for a formation flight. The giant XB-70 surrounded by smaller jets powered by GE engines. An F-4 Phantom, an F-5 Freedom Fighter, a T-38 Talon, and Joe Walker in his F-104. It was a vanity shot, a dangerous PR stunt. Flying close formation is difficult. Flying close formation with a massive experimental bomber that generates powerful wingtip vortices is deadly. As they flew over the desert for the cameras, Joe Walker's F-104 drifted too close to the right wingtip of the Valkyrie. The vortex, the swirling tornado of air coming off the bomber's wing, grabbed Walker's small fighter. The F-104 flipped over. It smashed into the top of the Valkyrie's wing. It sheared off the twin vertical stabilizers of the giant bomber. Walker's plane exploded instantly in a ball of fire. It was killed on impact. The Valkyrie, stripped of its tails, flew straight for a few seconds, then entered a flat spin. The massive white bomber fell from the sky like a dead leaf. One pilot ejected. The other, Major Carl Cross, was pinned by G-forces and rode the ship into the ground. A giant pillar of black smoke rose from the desert floor. In one morning, America lost two of its greatest pilots and two of its most advanced aircraft. All for a magazine photo. The loss of Joe Walker broke the heart of Edwards Air Force Base. He was the mentor, the leader, the man who had flown to space in a rocket plane and come back to tell the joke. The combination of the Valkyrie disaster and the Mike Adams crash cast a long shadow over the high desert. The swagger of the 1950s was gone. The right stuff was starting to feel like a grim duty. The pilots realized that they were expendable assets in a Cold War machine that demanded progress at any cost. Yet despite the funerals, despite the flags folded into triangles and handed to weeping widows, the survivors kept flying. Why? Because the data was critical. NASA was designing the space shuttle. They needed to know how a winged vehicle behaved during hypersonic re-entry. They needed to know about shock-shock interactions. They needed to know about heat soaking. The X-15 was the only laboratory in the world where they could test these things. So pilots like Bill Dana and Pete Knight climbed back into the remaining two aircraft. They flew missions that were arguably even more dangerous than the ones before. They tested new thermal protection systems. They tested new scramjet concepts. They flew with a grim determination. Let's look at the mechanics of survival in this era. How did a pilot actually escape a dying X-15? The ejection seat was a masterpiece of desperation. It was designed by North American Aviation to work at Mach 4 and 120,000 feet. It had two stabilizing fins that popped out to keep the seat from tumbling. It had a blast shield to protect the pilot from the windstream. But the pilots didn't trust it. Scott Crossfield, the first pilot, famously said he would rather ride the plane into the ground than eject. Why? Because at Mach 4, the air friction is a blowtorch. If you eject, even with a pressure suit, the heat pulse could melt your visor. The aerodynamic shock, the sudden deceleration from 3,000 miles per hour to subsonic speeds, would result in G-forces that could snap your neck, detach your retinas, and rupture your internal organs. The seat was a Hail Mary. The only time it was successfully used was by Jack McKay. Recall the crash of Flight 23152. The day the X-15 flipped over on landing, McKay didn't eject. He jettisoned the canopy after the crash, but he was trapped in the upside-down wreckage. The cockpit was filling with ammonia fumes. He was drowning in toxic gas. The rescue crew had to dig him out of the mud. He survived, but his back was crushed. He flew again in pain for years until the Air Force grounded him. The injuries eventually shortened his life. This was the reality of the right stuff. It wasn't just glory. It was chronic pain. It was spinal compression. It was hearing loss from the roar of the engines. It was the psychological weight of knowing your friends were dead. But there were lighter moments of pure, unadulterated pilot logic that define the era. Take the story of the skid test. The engineers were worried that the rear landing skids would dig into the mud and flip the plane, which eventually happened to McKay. They wanted to test them, but they didn't want to risk an X-15. So they bought a 1957 Ford pickup truck. They welded a spare X-15 landing skid to the back bumper. They drove the truck across the dry lake bed at 90 miles per hour, dragging the skid through the dirt, measuring the friction. It was low-tech. It was redneck engineering. And it worked. Or the story of the Plan B navigation system. The X-15 had an inertial navigation system, a complex computer with gyroscopes, but it drifted. It was unreliable, so the pilots developed a backup. They looked out the window. They memorized the geography of the western United States. If I see the Salton Sea on my left and Lake Tahoe on my right, I know I'm on the corridor. They drew grease pencil lines on the window of the cockpit to mark the horizon angles. If the horizon is at this line, I'm at a 10-degree pitch. It was the ultimate fusion of high-tech and low-tech, a multi-million-dollar rocket plane being flown by a guy looking out the window with a grease mark on the glass. By 1968, the X-15 program was winding down. The space race had moved to Florida. The Saturn V was launching. The Apollo astronauts were the new heroes. The dusty, hot world of Edwards Air Force Base was becoming a backwater. But the pilots at Edwards knew the truth. They knew that the capsule guys were spam in a can. A monkey can fly a capsule, Chuck Yeager famously said. Though he respected the men, he disdained the automation. The X-15 pilots were flying, they were stick and rudder men to the end. They were the ones who figured out how to bring a spaceship home to a runway. When the Space Shuttle Columbia finally launched in 1981, it was commanded by John Young and piloted by Bob Crippen. But the ghost in the cockpit was the X-15. The landing profile of the shuttle, the steep descent, the S-turns to bleed off energy, the flare at the last second was an exact copy of the X-15 approach. Every time a shuttle landed, it was paying tribute to the Black Bullet. But the most haunting legacy of the program isn't the technology, it's the lost astronauts. Because the X-15 was classified as an airplane, the pilots didn't get the same fame as the Mercury 7. They didn't get the Life magazine covers. They didn't get the Corvettes unless they bought them themselves. For decades, the Air Force pilots who flew above 50 miles were awarded astronaut wings. But the civilian NASA pilots, like Joe Walker, were not officially recognized as astronauts by the government. It was a bureaucratic technicality. It wasn't until 2005, nearly 40 years later, that NASA finally officially awarded astronaut wings to the civilian X-15 pilots. Most of them were dead by then. Joe Walker was gone. Mike Adams was gone. Jack McKay was gone. Their families accepted the wings on their behalf. It was a belated apology, a recognition that these men had gone to the same black void as Armstrong and Aldrin, but they had done it alone, in a cockpit filled with steam gauges, flying a machine that tried to kill them every time they touched the stick. As we approach the final chapter of our story, we have to ask, what was it all for? Was it worth the lives? Was it worth the millions of dollars? The answer lies in the data, but it also lies in the spirit. The X-15 proved that we didn't have to surrender to gravity. We could fight it. It proved that the atmosphere wasn't a wall but a door. And it proved that a human being, armed with courage and a slide rule, could solve problems that no computer could handle. In the final part of our journey, we will take one last ride. We will look at the final flight. We will watch the sun set on the dry lake bed. And we will say goodbye to the era of the rocket plane. The era when the sky was torn open by a black needle and the future rushed in. October 24th, 1968, the high desert sun is as relentless as ever, leaching the blue out of the sky. On the tarmac at Edwards Air Force Base, the B-52 mothership taxis out for the 199th time. Tucked under its wing is X-15 number 1, the original, the survivor. The pilot is Bill Dana, a NASA legend with a dry wit and a heavy foot. The mission profile is technically a test of a high-temperature horizon scanner. But everyone knows the truth. This is the funeral procession. The program has been cancelled. The funding has dried up. The space race has moved to the humid swamps of Florida, where the massive Saturn V rockets are preparing to hurl men to the moon. The gritty, grease and welding torch work of the X-15 is no longer the headline, it is yesterday's news. There was supposed to be a 200th flight. A nice round number to close the books. But technical glitches and snow on the dry lake, a rarity, would eventually scrub it. So, Flight 199 is the end of the line. Dana drops. He lights the XL-99 engine. For the last time, the thunder rolls across the Mojave. For the last time, a man rides a controlled explosion into the stratosphere. He hits Mach 5.38. He reaches 255,000 feet. He hangs there in the silence, looking at the curve of the earth, the black sky, the thin blue line. He is the last sentinel. As he shuts down the engine, the silence that rushes back into the cockpit feels heavy. It is the silence of a factory closing down, the silence of a tool being put back in the box. He glides back. He lands on Rogers Dry Lake. The skids dig into the clay. The dust plumes rise. The plane slides to a halt. Bill Dana climbs out. He pats the side of the scorched black fuselage. "That's a wrap," he says. "The X-15 program is over, but a machine like this doesn't just disappear. It leaves a blast crater in history, and out of that crater, the future emerged. To understand the true weight of the X-15, you have to look at what came after. You have to look at the space shuttle. When Americans watched the shuttle Columbia launch in 1981, they saw a white delta-winged spaceship. They were told it was a new kind of flying machine. But the engineers knew better. The shuttle was the child of the X-15. It was the X-15 scaled up, smoothed out and painted white. Every critical system on the shuttle was forged in the fire of the X-15 program. The heat tiles? The X-15 proved that ablative coatings and heat-soaked structures could work. The reaction control system RCS, the little thrusters that allowed the shuttle to turn in orbit, were direct descendants of the steam jets Joe Walker used to steer the X-15. The re-entry profile, the S-turns the shuttle pilots flew to bleed off energy without burning up. That maneuver was written in the blood and sweat of the X-15 pilots. And the landing. The shuttle was a glider. It had no engines for landing. It dropped from orbit like a brick with wings. The astronauts had one shot, no go-arounds. Where did they learn to do that? They learned it on the dry lakes of the Mojave. The dead stick, landing, gliding a heavy, unpowered brick to a precise point on a runway, was the signature move of the X-15. When Commander John Young landed the first shuttle, he was using the muscle memory of the X-15 generation. The black bullet didn't just break records. It built the foundation of modern spaceflight. It proved that you didn't have to be a passenger in a capsule. You could fly, you could pilot, you could bring the ship home yourself. And then there is the human legacy. Where did the men go? Some went to the stars. Neil Armstrong is the most famous alumnus. The world remembers him as the man who walked on the moon. They remember the small step. But watch the footage of the Apollo 11 landing again. Watch the last 2 minutes. The computer was guiding the lunar module toward a crater filled with boulders the size of Volkswagens. If they landed there, they would crash. Armstrong didn't panic. He didn't ask Houston for permission. He kicked off the autopilot. He took the stick. He flew the lunar module manually. He was low on fuel. He had seconds remaining. The alarms were blaring, but he wasn't Neil Armstrong, the astronaut, in that moment. He was Neil Armstrong, the X-15 pilot. He was back in the desert, managing energy, ignoring the danger, focused entirely on the vector. He skimmed over the rocks. He set it down gently. The Eagle has landed. That landing was a direct result of the lessons learned at 200,000 feet over California. The right stuff wasn't about bravery, it was about competence. It was about the ability to function when the warning lights are red and the fuel is low. Others stayed on the ground, but they rose high in different ways. Pete Knight, the speed king, went into politics. He became a state senator, but he never stopped being the man who flew Mach 6.7. He carried that fire with him. Bill Dana continued to fly test aircraft for NASA until the 90s. He was the elder statesman, the man who could look a young Top Gun pilot in the eye and say, "Son, I was flying hypersonic before you were born." And then there are the planes themselves. They are not gone. They are sleeping. X-15 number 1 hangs in the National Air and Space Museum in Washington, D.C. It is suspended in the main hall, the milestones of flight. It hangs near the Spirit of St. Louis and the Bell X1, but if you look closely at it, it looks different from the others. The Spirit of St. Louis looks fragile, the Bell X1 looks pristine like a toy, the X-15 looks like a weapon. It is scorched. The black paint is faded in spots. The Inconel skin is rippled from the heat. It looks used. It looks like a hammer that has hit 1,000 nails. It is a monument to a time when we weren't afraid to build things that were dangerous. X-15 number 2, the fast one, the one that wore the pink foam, is at the National Museum of the United States Air Force in Dayton, Ohio. It has been restored to its black livery, but underneath, the frame is scarred from the day Pete Knight nearly melted it. And X-15 number 3, the one Mike Adams died in, it is gone, buried in the desert. A memorial to the price of admission. As we look back from the vantage point of the 21st century, the X-15 era feels almost mythological. We live in a time of safety. We have risk assessments for everything. We have safety officers. We have endless meetings to discuss liability. We have grounded fleets because of a single sensor failure. We are careful, and being careful keeps people alive. That is a good thing. But the X-15 era asks us a hard question. Have we lost something? Have we lost the willingness to accept risk in exchange for progress? The men of the high desert accepted that people would die. They didn't want to die. They fought like hell to live, but they understood that if you want to go Mach 6, you can't guarantee safety. They operated on the principle of calculated risk. You do the math. You build it strong, you train the pilot, and then you roll the dice. Because if you don't roll the dice, you never leave the ground. The X-15 was the ultimate expression of American engineering confidence. It was built in a shop in Los Angeles by guys with cigarettes hanging out of their mouths, welding exotic alloys by hand. It was flown by guys who drove Corvettes and didn't wait for a computer to tell them what to do. It was raw. It was mechanical. It was real. There was no fly-by-wire to save you. There was a steel cable connected to a hydraulic valve. If you pulled the stick, the plane moved. If you pulled it too hard, the plane broke. It was the ultimate relationship between man and machine. Tonight, the Rogers Dry Lake is quiet, the B-52s are gone, the sonic booms have faded. The coyotes hunt in the sagebrush, undisturbed by the thunder of rockets, but the ghosts are still there. If you stand on the lake bed at sunrise, when the heat waves are just starting to shimmer, you can almost feel it. You can feel the vibration in the ground. You can smell the ammonia and the burnt rubber. You can see the black shape dropping from the sky, trailing a diamond of white fire. The X-15 was a brief moment in time, a 10-year window where we bridged the gap between the atmosphere and the stars. It was the hardest flying human beings have ever done, and they did it with a grin. Think about the pilot one last time. He has landed. The plane is ticking and pinging as it cools. The rescue trucks are pulling up. He unbuckles his harness. He disconnects his oxygen hose. He lifts the canopy. The desert air rushes in. It is hot, dry, and smells of dust. He takes off his helmet. He is soaked in sweat. His face is lined with the imprint of the oxygen mask. His hands are shaking slightly from the adrenaline crash. He climbs down the ladder. He stands on the hard-packed clay. He looks up at the sky he just fell from. It is blue and empty. He has been to the edge of the world. He has seen the black void. And he has returned. He lights a cigarette. He takes a drag. He nods to the crew chief. "She flew good today," he says. "She flew good. The black bullet is at rest. The war on gravity continues, fought by new machines and new men. But the X-15 remains the king, the fastest, the highest, the hardest. A machine made of steel and nerve, a testament to what we can do when we are willing to push the throttle all the way to the stop, when we are willing to ride the fire. The flight is over. The engine is cold. The hangar doors are closing. But the echo of the roar remains. It remains in the roar of every rocket that leaves the pad. It remains in the heart of every pilot who looks at the sky and wonders, how fast can it go? Good night from the high desert. Mission complete.